Okay, welcome to class meeting 13 of EECE574, the graduate level probability and random processes. The first announcement is one of the most important announcements. So you will be taking the midterm exam next Thursday. So you have 1 week here at 7 p.m. to 10 p.m. Open everything except any human interactions among you or among your family. No human interaction is possible. Got it? Homework 10 will be assigned, and handouts and video lectures are available. Next one is clarification. So last time, I used a complex random variable with variance sigma square, and at the same time, I used a complex random variable with variance 2 sigma square. So let me write it here, 2. And since x is confusing, let me correct it to z. Where is z? Okay. Z. And what's the difference? Just scaling of the random variable. However, you must be careful. Here, if you decompose this complex Gaussian random variable into real and imaginary parts, each one has variance sigma square over 2 in this case. Here, your variance is sigma square. Got it? So when you use Q function, for example, then you must be careful. When you use Markham's Q function or generalized Markham's Q function, you must be very, very careful. So let's see. First, I define the Q function for the right tail probability given a real Gaussian random variable, right? So let's think about this probability of event that absolute value of x is real Gaussian, because this is n, not Cn, right? And greater than or equal to r. And if you instantly visualize the density function of this x and the interval you are interested in, what happens? This event has 2 intervals, right? And the right interval is related to this one, Q of r minus mu, the mean, divided by sigma. Also, left tail is related to that one. Am I correct? Just a second, something's not correct. Okay. Yeah, I'm wrong. Sorry about that. The sign is not correct. Sorry about that. So sign should be changed. So the second term is Q of r plus mu divided by sigma, if I'm correct. So what? It's a function of mu over sigma and r over sigma. Here you see this is r over sigma minus mu over sigma. And here this is r over sigma plus mu over sigma, right? So you can view the Q function, you can view this probability as a function of kind of normalized version of the mean and normalized version of your radius, right? Now, let's remember the real Gaussian random vector case, where mean is in general a non-zero vector, but the components, each element of this length 2m real random vector has variance sigma square. In that case, if m equals 1, we use Markham's Q function. If m is general integer, then we use generalized Markham's Q function, where since each real Gaussian has variance sigma square, we have first parameter mu, the norm of mu, 2 norm of mu, which means that the length from the origin to mu divided by sigma. It's not R. And also, you have normalized version of your kind of radius or distance divided by sigma. Got it? So here, sigma appears. Now, this is tricky question. Here you have a complex Gaussian, proper complex Gaussian random vector with complex valued length m mean vector, and the covariance matrix is 2 sigma squared times identity. Now, I'm asking you to compute the probability of event that the 2 norm of z is greater than or equal to r. Then, in terms of the generalized Markham's Q function, what is your answer? What is your answer? You can kind of convert this one to x, real Gaussian, real of mu, and imaginary of mu. And then what? What is the covariance matrix? Sigma square, I to m. So you go back to this case, right? The only difference is that the mu equals norm of real part of mu squared plus imaginary part of mu squared of square root. Got it? So what is this? The answer is Q sub m mu, 2 norm of mu divided by sigma, and here r divided by sigma. So the same, right? Now, what if I slightly change the covariance matrix to sigma squared? Then your answer must be Q of, be careful, here complex Gaussian has length n, which means that real Gaussian has length 2n, right? But in Markham's Q function, you put that n, so here goes n, and mu over, what is the variance of each real Gaussian? Sigma over square root 2, because variance is sigma square over 2. And here are sigma divided by square root. Got it? So I want to emphasize that you should not be confused, okay? Whenever you have difficulty, just convert everything to real, okay? That is the philosophy or idea of what? The real composite vector. So given a complex valued random variable or vector, you just convert it to real of z and imaginary of z and have a real vector. That is the idea of real composite vector approach. Got it? Next. Let's elaborate a little bit more. So here you have, let me change it again to C. And precisely speaking, this is a Z vector. So proper complex Gaussian random vector Z has mean mu vector. And again, sigma square times scaled identity. Then any direction among 2m real directions. So even though this is the length n vector, if you convert it to a real composite vector, then what? You have 2m real Gaussians. And any direction is real Gaussian and variance sigma square over 2. Okay. Interesting thing is that if you rotate the coordinate with respect to the mean, then still what? Any direction, any real direction has variance again sigma square over 2. That's why we had some strange results like this one, right? You have mean vector and you have some constant vector, and you want to find the probability of this event, and it can be written simply using Q function, because what is important is a single real direction after rotating the axis. Got it? By the way, I have found one mistake in my old lecture note, even though I didn't mention in the last class meeting. But anyway, probably my handout has this figure, but it is wrong. So I should correct this into this Venn diagram. So given the set of all complex valued random vectors, you have the subset of proper complex random vectors, and you have Gaussian, complex Gaussian random vectors. And then the intersection is proper complex Gaussian random vectors. And this intersection has some random variable, for example, z, that is denoted by what? Cn, some mu, and some covariance matrix. Got it? Okay, so I believe I'm done. Let's overview the entire course and let's find where we are. And here, this is the topic from today, time average and ergodicity. So we have been actually very slow compared to other 574 courses in the previous years. Probably you've heard that, or you've heard from your seniors in your lab that other professors and even me cover the topics very fast. But this year, I decided not to cover the random variables and vectors part or reduce that part as much as possible, but focus on random processes part, because I found that almost every year when I teach 574 that I had no time to cover the random process part in depth. And so anyway, so this is today's topic, time average and ergodicity. And I have found that the Peebles textbook and even the Populist textbook is not that friendly. And you may say that my lecture is not friendly either, but I will try my best. So this is preview. We are talking about inference and statistical inference, statistical signal processing and random observation, detection estimation theory. That is actually EECE574. Statistical signal processing. And I will talk more about observation of single sample path versus statistical inference. And then we will talk about time average and ergodicity. By the way, I have to quickly review this part. There is no confusion, but first, what is the answer to this one? Why are we interested in complex valued signals and random processes in radio communications? As I told you, we apply real valued bandpass signal to the antennas that converts the electrical signal to radio signal or vice versa. So we handle real valued bandpass signals, and real valued bandpass signal has what? Has some complex baseband signal that is equivalent to the real bandpass signal. So it's much easier to handle the complex baseband signal. That's why we naturally have complex valued signals and processes. Now, why sometimes, not always, proper complex random processes are important? Because if you have some additive noise in your observation, and that is, for example, Y-sense stationary Gaussian. Suppose this N of T is real bandpass Y-sense stationary Gaussian, or just simply Ysen stationary random process. So if this is Ysen stationary, then what? Then our conclusion is that this is proper complex. I didn't show it, but actually it's not that difficult to prove this. But the proof or justification will be deferred until we study the power spectral density. So, okay, anyway. By the way, why I talked about widely linear processing? Because the idea is this one. We want to build an electrical system that is mathematically modeled somehow. The simplest system is what? The input is linearly mapped to the output, or linear plus some constant, which is a affine transform, right? But given complex valued input vector, is it the simplest? Yes. However, after the simplest one, what would be the next simple one? That is widely linear system. So there are two types of widely linear systems. One converts this Z into what? Real of Z and imaginary of Z, and just process linearly. Because now the input is real, right? The other one is that you convert it to what? Z and Z conjugate. And then you process linearly. These two systems can be equivalent if you carefully choose the matrices appearing in the upper box and lower box. Got it? And this processing is called widely linear processing. This is different from Z directly processed by some linear system, especially when Z is improper. Got it? And why improper signal is important? Even though real bandpass Ysen stationary random processes are converted to proper complex baseband random processes, there are many man-made signals in this radio environment that cannot be well modeled by a Ysen stationary process. That is, sometimes, I'm not saying that always, some man-made real bandpass signals are better modeled by improper complex Gaussian, improper complex random processes if you take the complex envelope. Got it? Anyway, review is done, and let's see this one. I kind of spent many minutes to update my lecture note. So we are back to section 2 of chapter 6 of the Peebles textbook. So here, as I mentioned, the EECE574, even though it's a 600 level course, a numbered course, actually when I was a graduate student, this course was a 500 level course, which meant that it was for the master's graduate students. The reason why I got 600 level is that when I came here to postdoc, there was no statistical signal processing course. So the professors asked me to open this new course. So I opened and tried to find a good number in 500 level. At that time, the numbers were depleted. So I got 600. But anyway, the difficulty would be more than ordinary 500 levels. But this course was one of the most important course when I was a graduate student. Anyway, so here, the title of the course sometimes is named as Statistical Signal Processing, or in some universities, it is called Detection and Estimation Theory. But the commonality is that this course talks about statistical inference. And many of you may say that, wait a minute, is it the task to be done by so-called machines and artificial intelligent models? Yes. Actually, what is intelligence? We have to ask that. it's a capability to infer something. Sometimes it's a logical inference. Sometimes it's inference based on experience. But inference based on experience that is mostly tackled by these AI models are actually what? Statistical inference, if we mathematically approach that. So this course is very closely related to the machine learning and artificial intelligence. The only difference is that we are not much concerned about training part. In this course, we usually give the exact statistical model of our observation. And then we just design this system. However, in the machine learning and AI, we usually are given many realization of observations. Based on that, we have another system, not this one, another system. So that accepts this many observations and optimize parameters of this inference system. That is the training part, okay? So the idea is not that different from the machine learning, but anyway. So common signal and system model in statistical signal processing is this one. Sometimes you are given a source that generates some parameter, a known parameter. And then this parameter is mapped to random observation. So this is a probabilistic or statistical mapping rule. And then you observe, as a system, you observe this one. And then what you do is that you infer something from this one. Usually, you infer about this hidden parameter. And then generates the output, and you have a sink, okay? Or sometimes we just combine these two. Anyway, we only observe that one. So given Y, we want to find out some governing parameter theta using this inference system. Got it? So this is the task of the statistical signal processing and also machine learning and artificial intelligence. We want to build an inference system. Got it? What is important is that this has uncertainty. So one of the mathematical approach is to use probability theory. So we model this as a random observation. And even though I just use theta hat, sometimes this output of the inference system is the interval where this true value resides. Sometimes a single parameter having the same unit as this parameter. In that case, we call this as a point estimate. So sometimes we generate point estimate, sometimes we generate interval estimate. Another one is this one. So here, what is important is also where this set included. So when we want to find out or infer or guess the value of theta, the theta as a member of some set, that set would be a countable set or an uncountable set. For example, here I toss a coin. And then I somehow map randomly to the output. And based on the observation, you want to estimate what was the result of coin flipping. In that case, theta is a member of some set, right? That is what? That is heads and tails, so it's a finite set. However, for example, if I spin a needle and measure an angle, and then I add some noise and give it to you, then what? You have to guess theta. That is an element of the interval. And that real interval is an uncountable set. Interestingly, whether that set is countable or uncountable makes huge difference in statistical inference. And we have a totally different approach, apparently, and very different structure in the inference system. So we divide our statistical inference problem into two. One is detection or classification problem when we have countable set. If we have uncountable set, it's called estimation problem. However, estimation itself sometimes includes detection too. Okay, so in a narrow sense, estimation is not detection. But in a wide sense, estimation means inference, statistical inference. Got it? So if you take my course, I don't know when I open this course, but the course is divided into 12 subparts. And first, I divide the entire course based on the observation. So random vector observation. Here, random observation is vector. And then sequence or discrete time signal. And then here, continuous time signal. Because we need some kind of pre-processing, or sometimes we have totally different criteria when we have a vector or some signal. So I usually divide the course into 3, and then, so this is related to the random observation. And what is important? Hidden parameter. So parameter is in a set, and what is this one? So here you have detection problem and estimation problem, detection problem, estimation problem, detection and estimation. So now we have 6. And here goes one more. This hidden parameter is a member of that set. And sometimes we may have more than that information, whether that X is a countable set or an uncountable set. Sometimes we probabilistically model theta. So theta is sometimes a random something. Theta could be random variable, random vector. So that is also very important. So here, theta random, yes, no, yes, no. And then how many? 3, 2, 2, so 12 parts. But as far as you understand the first 8 parts, then the rest of it is kind of very straightforward. So that part is very, very important. Anyway, the reason why I talk about this is in this 645 statistical signal processing, usually we assume this. The family of distribution functions, f of random observation parameterized by parameter theta, is completely known. So let's see this. Here, what that means is that this part is known. What does that mean? How the theta is mapped to y is known. We assume that. Got it? But that assumption is sometimes very, very dangerous. See that? Given theta, so given theta, the y has different density in general. So you have to parameterize the density of y by theta. So if you change theta, you have different distributions. For example, if suppose theta is either 0 or 1, and your output, random output y, is that you add some zero mean Gaussian noise to that value. So y equals theta plus noise Gaussian. Then if theta equals 1, then what is the distribution of y? So If theta is 1, then y parameterized by theta is what? Gaussian with mean 1 and variance sigma square. So suppose 0 mean sigma square, right? If theta is 0, then y theta is 0 sigma square. So you have different density, right? Parameterized by this parameter theta. But in that problem, these two density functions, so this density and that density is in this set is known to us. And then we solve some problem. If we have random parameter, not only this one, we also know, for example, the density of theta, in addition to the family of distribution functions of the random observation. Okay? But anyway, whether it is estimation problem or detection problem, in statistical signal processing, most of the times we assume that this family of random observations parameterized by theta is known. Okay? You are given that. Unlike 645, in most of the machine learning problem, you are not given that distribution. That's why you somehow need to find that distribution. And based on that, you optimize the parameter of your machine learning model. That is the procedure of training. Got it? So training is actually involves extracting some statistical model of your observation. That's why if you read many books about machine learning and artificial intelligence, statisticians have written that book. Okay. Anyway, so after we are given the observation model, what we do in estimation detection theory is to formulate an optimization problem. We want to design as an engineer. That is optimal in some sense. That is best in some sense. That is optimization, right? And then we solve. And eventually, we analyze the performance of our solution. So usually, signal processing, that is also statistical signal processing, these papers, research papers or books, what they do, they provide you signal model, signal and system model. And then they formulate the optimization problem. And then they solve. They teach you how to solve. And then eventually they plot the performance curve. Sometimes receiver operating characteristics, sometimes error probability curve. Got it? So you need the knowledge on this course, probability and random processes, to tackle any statistical signal processing course. The problem is that every statistical inference is about actually ensemble average. What does that mean? Ensemble average means expectation of something. And you may wonder, wait a minute, why detection problem is about ensemble average? For example, I have tossed a biased coin with probability of tails is 1/4 and the heads is 3/4. And you observe some random mapping of that and want to infer what was shown. And you may say that, I remember that is the map detection problem. So I compute the maximum a posteriori probability of seeing some observation, probability of heads given that observation and tails given the observation. I'm not dealing with expectation. I'm dealing with probability, you may say. That is very dangerous because any probability of event can be written as the expectation of the indicator function with parameter, that event. So actually, when we talk about probability, we are dealing with ensemble average. And ensemble average means we somehow assume that this experiment can be repeated independently many times. Otherwise, that expectation does not make sense, because what is the most important relation between expectation and our experience is that somehow we replace expectation using some arithmetic average, which means what? Law of large numbers we rely on. So we rely on law of large numbers, conceptually or formally. Got it? And here comes the dilemma. Sometimes, especially when we model our observation as a random process, we usually say that, okay, here is a continuous time random process x of t. Here, t can be any real number. Then, as I once told you in this course, what does that mean by plus minus infinity? Precisely speaking, that if that is observed, that a single, we observe that random process, we can only observe a part of that realization of this random process. So precisely speaking, we are given some x of t of s. And here we have a sample space probability, sample space, event space, and probability measure that models a random experiment generating the outcome S. And then here is a mapping rule that maps each S into a continuous time signal that spans entire real line. And then here we observe the output. Then what happens? If we follow that measure theoretic model and we literally take negative infinity and positive infinity, then what happens? We can observe only a part of a single realization, right? Here sometimes S0 is realized, right? And probably we observe part from 9 a.m. today and 9 a.m. 5 seconds, right? As an electrical engineer, we build some system and that system observe only 5 seconds. Or if you really want, that is EECE574 2024 something, right? We can observe only a part of a single realization if we literally interpret plus minus infinity. There is no ensemble average, right? Of course, we can start from the assumption that we are given the entire family of random processes. But as I told you, sometimes even that assumption does not work, and I will show you the example. Suppose we have modeled that our random observation y of t, the continuous time random process, is some r times cosine 2 pi f0 t plus theta. And now you are this is very familiar with it, right? And given that r and theta are random variables. So actually, the random process is constructed using 2 random variables. Now, question. Given a single realization of, let me see, y, right? This is y, x. Let me just say this x, okay? Because every other things are x. So this is event, okay? It's like x is x, right? This is an event. So the random variable realization. Similarly, random process, some deterministic function that is realized. So some x of t is realized, but you observed during the interval 0 to t. Now I ask you, what would be, so predict, right? That is very important, right? Prediction is the key in our intelligence, right? And also inference. So given that, I ask you to predict the value of x at 2t. And you have this model. What is your value? And you know that since there is no noise here, if you observe some realization, so this one, x0, can be written as r of 0 cosine 2 pi f0t plus theta 0. And here probably I have to assume that theta 0 is not 0. But anyway, that constant is known. Okay. Then you can find r0 theta 0 with 0 error, mathematically speaking, right? And then since you know r0 theta 0, you just plug in capital T, 2t here, like this, right? Then you have x of 2t perfectly. No ensemble required, right? However, if I slightly change the problem like this without literally interpreting that plus minus infinity, I may assume that, okay, as we engineers, negative infinity may mean 9 a.m. every day. Positive infinity may mean 9 a.m. 5 seconds every day. Now, I may be asking you that you have observed today the realization of random process for 5 seconds, okay? And then I ask you, okay, tomorrow or the day after tomorrow or for 300 days, what would be the value of random process at time 9 and 10 seconds, 9 o'clock, 10 seconds, based on your observation today? That is this question. Given the realization of random observation, predict this random process at t equals 2t. So you get the idea, right? Literally, you cannot ask this because anyway, we live once. And mathematically speaking, we can only observe a single realization. There is no ensemble. Even though there is some ensemble average, we cannot handle that. Impossible, right? So see this example. Suppose you observe this random process for 0 to 2t. And I ask you, what is the probability, first order probability distribution of this random variable, capital X of 2t? Can you answer? You observe only this one with some specific r0 theta 0 for t, 0 to 2t, 0 to t. And there is no way to predict that, right? No statistical inference possible in this case. Got it? But in many cases, that is the real problem in our especially stock market prediction, right? Suppose you want to predict the price of the one stock in, what is the popular one? Yeah, EcoPro BM. You know, probably some of you are interested in stock market, and EcoPro BM, that company's stock sold almost twice during last 3 months. Okay, so anyway, you want to predict what will happen tomorrow. So if you believe tomorrow, or with high probability that this will rise 20% point tomorrow, then you have to what? 연끌 해야죠. Okay. You have to collect every possible your resource and buy that stock. But that never happens, right? We only observe a single random process, literally. However, we know that stock market opens 9 a.m. and closes 3:30 p.m. every day, every weekday. And you may say that, okay, let me interpret negative infinity. I don't need negative infinity and positive infinity. Anyway, I may assume that this random process can be observed every day. So I may observe many sample paths. And then I can do some ensemble average, right? And I can make some statistical inference, meaningful statistical inference to get some money, right? So literally speaking, mathematically speaking, this random process that spans entire line is very troublesome, right? Anyway, no inference possible. So statisticians have developed some idea. Here goes the idea. They define, so given the set of all random processes, let's say continuous time random process, you define a subset of random processes. Actually, this set is very, very small. I exaggerated size as always. And they named this set is the set of ergodic random processes, 또는 ergodic random processes. And I never actually tried to find the root of this term. But today I asked the Bing chat. And it says that Boltzmann, the physicist, first coined this term based on Greek letters. Ergon means work, and hodos means pass or way. Okay, some path, I don't know, but anyway, usually ergodic means now that from a single path or only a few of sample paths, you can get some information about the ensemble. Got it? That is the simplest idea. From only a few observations of sample paths, you can do some statistical prediction, or you can do some expectation. Got it? That sounds okay if you do not think deeply, but that is very strange. For example, let's go back to this one. From a single observation or observation of two sample paths, can you do statistical inference? Still no, right? So definitely there are many random processes that are not ergodic at all. Then how do we know whether a random process is ergodic or not? Actually, it's not easy. Okay? Sometimes we assume, okay? We assume the random process we are dealing with is an ergodic random process. And happily, we just under that assumption and a single observation, we make statistical inference saying that, okay, so I am not going to model the stock market change as a single random process. I do not like that because I want to sell my idea to buyers and saying that, okay, if you use my investment robot, then robo investor will give you higher interest than any other financial product, something like that. And what you can only do is what? Probably you may say that, okay, plus minus infinity is just for technicality. I may assume that something is repeated. So based on previous history of stock market, I will assume that I can predict because the stock market is an ergodic random process. Does it sound dangerous, right? Because people say that history repeats, and many people say that history looks like repeating, but never repeat in the same way. There is some pattern, but not exact, right? Anyway, we need some assumption to mathematically handle such a situation. So ergodic assumption is very, very strong. However, sometimes there is no other way to handle a random process. So for example, if you abandon the path as an electrical engineer and to go to some financial engineering part because you are equipped with math and knowledge on random process, never forget this, okay? Ergodic assumption is useful, but has its own limitation. So you must be careful. You should not fully rely on your assumption. Got it? Anyway, we will see in this lecture many time averages. And that time averages are linked to statistical averages. That is somewhat strange. Is it the only ergodicity definition? Sometimes it seems, but precisely speaking, it is not. However, as you will see, linking time average with statistical average when we talk about ergodicity, that idea is very useful. We will see. So here goes an example you already know. Suppose n sub t is a Poisson process. You know the sample path, right? And then here goes the problem. The arrival rate is unknown. But you observe a single path for positive interval. Okay, 0 to t. For example, suppose you assume that your Kospi index, the by order, arrives following a Poisson process for a very short time period. Even 1 or 2 seconds, if that stock is very popular, more than sometimes 100 orders are given, right? But anyway, you may assume that, okay, for 1 minute, this arrival process can be well modeled by a Poisson process. But you don't know the rate, right? You want to estimate that rate, and then you want to do something. For example, you've seen that price will go up because if it continues to have that rate, in 30 seconds, the price will go up. And if it continues for 1 minute, the price will go up and up. Then what can you do? If your if your tax and some portion of the money that must be go to the stock company, even though that kind of overhead, if you can earn some money in 1 minute with high probability, what will you do? You must buy that stock right now and wait for 2 minutes and then up and up. And if you sell successfully, then you get money, right? So estimating the arrival rate would be very important in that model. Now, what do you know? So n sub capital T is what? From 0, some reference time 0. And let's say this is 60 seconds from now on. And you count the number of orders, arrivals. And then you divide simply, and then you know that let me say, yeah. Let's define expectation of n of t divided by t. Let's say that is lambda, okay? And then you can easily show that that goes to, let me see, is it correct? Something's, yeah, I have to remove that, okay? Let's say that lambda hat sub 1, our first estimate of lambda is just simply that one, okay? You observe the number of arrivals, total number of arrivals, and divide by t. And this estimate, interestingly, you will see from this lecture, converges to lambda in the mean square sense. And you know it converges because the mean of lambda hat is lambda, and the variance of lambda hat is lambda over t. You can compute that. And if you want, I will put it in the midterm, so you will do it anyway. And then t goes to infinity means variance goes to 0, and your estimate converges somehow, we don't know yet, to true value. So in that case, if observation interval is large enough, so for sufficiently large observation interval, actually, we do not know what is that number exactly. Anyway, this is a good estimate. Another one is that one I wrote on the right side of the board. We convert the arrival process under the Poisson assumption to what? To an arrival process or an inter-arrival process. So let's say that our inter-arrival process, that is discrete time process, is x sub n. And if the n of t is Poisson process, its inter-arrival process is what? Consists of IID, exponential random variables, with parameter lambda. Means its mean is 1 over lambda. So you are kind of want to use law of large numbers. So other than using n sub capital T, suppose you have 100 of arrivals, then you calculate the inter-arrival times. That would be 0.2 seconds, sometimes 2 seconds, 0.1 second, something like that. And then if you average that inter-arrival times from the law of large numbers, you already know, not precisely, but you know, right? And you divide by n, and here, let's say, and then it goes to 1 over lambda. You know that. So as you will be learned, you'll be taught in statistical signal processing, one of the method of moment estimator is simply you divide n over t by the sum of inter-arrival times. And you can show that this also converges to true value lambda if t is large enough, or it depends on ratio. But anyway, the question is which estimate is better? Because you want to have a better estimate, right? Given the short period, you want to estimate better so that your decision is better made. And that kind of thing is very important, right? But I'm not going to talk about that today, probably in the midterm. Anyway, so what I want to say is that, is this involves any time average? There is no time average, right? But somehow you can extract information about arrival rate in the Poisson process. Single parameter governs, that is the arrival rate, right? If you know the arrival rate, you know everything statistically about the process, right? And this information can be extracted from a single path if your interval is large enough. That is good, right? It seems that we want to say that this Poisson random process is an ergodic process in some sense, because we can extract lambda from a single observation of single realization, single sample path. Got it? But usually, in this course and almost every textbook, they say that, okay, ergodicity is about relating time average with statistical average or probability sometimes. And actually, we can do that because if you remember sample path over Poisson process, then what? This, if you differentiate this with respect to t, then what do you have? You have delta functions, right? Sum of delta t minus arrival time, right? We've seen, sorry about that, u of. We've seen this representation, right? We have unit step functions delayed by arrival time s sub n, right? And then, what is n of t in terms of, for example, n prime of t? Let's say that that is the differentiation of n of t, random process. We haven't yet defined, we haven't yet talked about stochastic calculus yet. Stochastic calculus means that calculus involving random processes. We haven't yet talked about that, but anyway, that is simple, right? Because we know, sorry about that. Let me be quickly fix it, okay? So n of t equals sigma u of t minus Sn, and n prime of t is sigma n delta of t minus S, right? So n of t can be actually written as what? The integration of n prime of t, right? If you integrate n prime of t, then you have n of t. So actually, what we do is that we convert our observation to an equivalent random observation, and we use time average. We integrate over time. If you scale this by t, this is what? Time average over signal. So it seems that people's conventional wisdom saying that ergodicity is about linking time average and statistical average seems okay, even in this example. Apparently, there is no time average, but if we consider n prime of t, the differentiation of our Poisson random process, then actually we have been using the time average. So anyway, from this point, I will just talk about time average and statistical average to talk about ergodicity over random process. Got it? Now, first, we need to define what is time average over signal, not random process, because that is easier. And also, when we handle a sample path, anyway, sample path must be time averaged, for example. But this one looks strange, but anyway. So here goes the time average or the mean value of a continuous time signal. It's not random process yet, okay? So x of t is defined as what? As the limit of an integral. So here goes the limit, and here goes the integral. So it can be said integral of x of t divided by 2t, or after you integrate, you divide by 2t. Okay? What is that, by the way? So whenever you have time average, just have this mental model, simplest example. Think about a constant function. Suppose you have a constant function, x of t equals c for all t. What is the time average? So you have some function c, right? You average over negative capital T to positive capital T, then integral is what? C times 2t. Now you divide by the interval to get back the value. So this holds. Okay? If you have a constant function, time average is simply the constant value itself. Suppose you have some cosine function plus some constant. Now you calculate the time average. Then, as you've seen in 수학의 정석, depending on capital T, value differs. However, if you let t tends to infinity, right? What is the average? That constant, because that oscillation cancels and goes to 0, right? So it's kind of an operator that extracts the so-called, as an electrical engineering, we say that a DC term, right? So this is a DC term extract, right? It extracts the DC component of x of t. You can interpret it like that. Got it? Now, why this is that important in random process? First, think about some little bit different topic. What is the energy of a continuous time signal x of t? Suppose you are given a signal x of t, and I'm asking you to compute the energy. And you may say that, no. Energy has the unit joules, and you didn't provide any unit for x. You're right. So without talking about the unit of the real world signal, we cannot define energy. However, even in that case, mathematically, we define the energy of signal simply x of t, if it is real, absolute value squared, or if it is complex value, it's modulus squared, integrated over the entire real line. And now, as a student who took my course this year, you know how to interpret this plus minus infinity, mathematically or practically, right? So this is the energy of the signal. And one of the important facts professors do not usually teach in signal gen systems is that we have handled finite energy signals most of the times, which means that this energy is finite. This means finite, okay? And also, if the energy is positive and finite, then we call the X is an energy signal or simply finite energy signal, okay? But anyway, energy signal. Why energy signal important? Mathematically, that signal is called L2 function, which means that square integrable function. And if the signal is square integrable, you have very good Fourier Plancherel transform. And actually, the Fourier transform you learned in your signal gen systems was most of the times was Fourier Plancherel transform. Anyway, and also you have parsevise relation saying that if your Fourier Plancherel transform is capital X of F, this energy can be computed in terms of your Fourier Plancherel transform. Got it? The problem is that as an electrical engineer, sometimes we have to model our signal as an infinite energy signal. The most representative example is a signal passing through power line. We just model as a cosine function or sine function, right? And that function, unfortunately, is not a finite energy signal. Its energy is infinite, right? If you integrate over the entire period, suppose you have cosine 2 pi f0 t. If you square and integrate, what happens? It goes to infinity. It's how average power is then. However, what is the average power? If you compute average power of the cosine function, what is that? 1/2, right? If you square it, then you have this 1/2 plus cosine 4 pi ft ct. Then you find the dc, you have 1/2, right? So it seems that we need some different definition than energy. That is power. Got it? So power over continuous time signal, x of t, is defined as, first, you compute the energy within a finite interval. And then you divide it by the length of the interval, which means that energy divided by second, which is power, that is the average power within this interval. And then you take t to infinity. Here, be careful. Mathematically, t goes to infinity, but practically, you just take t sufficiently large value. Got it? And if this value is finite and greater than 0, x is called a power signal. So let me ask you a question. If a signal x of t is an energy signal, what is the power of that one? 0 in general, right? Because you have this term, right? And if a signal is a power signal, means power is finite and positive. What is its energy? Infinity, okay? One of the reasons why people exclude 0 is that because if they do not exclude x of t equals 0 for all t, is an energy signal and also power signal if we do not remove that one. Got it? Anyway, what's popped up? What is this? Okay, 한컴 자동 update. Okay. So now you may wonder then this union of energy signal set and power signal set would be the entire signal set. Actually, it is not. Okay, it is not. Okay. Some signal, mathematically interesting signal, but not practically, has what? Infinite power. For example, x of t equals exponential T. That has what? Infinite power. But that would not be interesting for in engineering sense. Anyway, so we have defined the term energy over deterministic signal and the power over deterministic signal. Okay? And before we move to the next page, this is also very important. Suppose you have some signal x of t, and then you compute, here, yeah, let's do this. So suppose you are given x of t, a finite energy signal. Suppose x of t is finite energy signal. Now, you define y of t as delayed version. Then what is the energy of y? If you plug this here, and after change of variable, you have the same thing. So this is an important lesson. If you compute energy of a signal, then any delayed or advanced version of that signal has the same energy, right? And that also holds for power case. So this is the translation invariance of energy operator. And also you have the same thing, translation invariance of power operator. So you suppose you have some operator that computes the power of your signal. Then if you delay the signal, even if you delay the signal, power is the same. Now, related concept is time autocorrelation function. I told you that this course, this semester, this year's 574 is mostly for communication engineers. Now, suppose you compute this one, and this looks horrible, but what is this? This is simply the time average of x of t plus tau and x conjugate of t. Or you may say that, okay, that does not look good. So let me do this. This is time average of x of t, x conjugate t minus tau. Okay. Now, you remember the definition of time average. That is what? Integration. You take some interval, okay? And then take the limit, dt, and you put that argument of this operator here as the integrand, right? So you have x of t, x conjugate of t minus tau. Now, why did I say initially these two are the same? Why? Why? Translation invariance. So suppose you delay x by tau. What happens? This becomes t, and this becomes t minus tau. So when you write time average of x of t plus tau x conjugate t, you subtract the argument. The right argument from the left and right argument from the left, if they are the same, they are the same time average. What can you do? You may subtract 1/2 of tau, then it becomes like this, right? Sometimes people love time autocorrelation defined in this way. So they use something like this. Advance your signal by tau over 2 and delay your signal by tau over 2 and take the conjugate and you integrate with respect to t and take capital T tends to infinity. So there are many different definitions, apparently looking different definitions of time autocorrelation function given a continuous time signal x of t. However, the commonality is that if you usually you put conjugation on the right factor. Okay, the reason is that when we extend this idea to vector valued random process, Hermitian transposition is usually used, and we compute outer product, not inner product in general. So putting conjugation on the second factor is much better and consistent. And you subtract and you get tau. You subtract, you get tau. you subtract, you get tau. So they are the same time autocorrelation functions of x of t. Anyway, time autocorrelation function is also a time average over function. Got it? So this time average appears again and again in electrical engineering, communications, and radar signal processing, and other things. Okay, let me stop here and continue more next time. That's all for today.